So I just now noticed that the aspect ratio is long and the slides are a little clipped off. So we will just go with that and hopefully it will not be too intrusive. So it was a great pleasure to be here. Some of you may know I did my undergrad here, and biking over here from my friend's house, once again, the campus has changed so much that I almost get lost coming down this thing. I don't think Terman Engineering is there anymore. It's like, that's very sad. Yeah, I saw that pit and I said, "Oh my God, I think that used to be Terman." So that was my childhood here, all gone. So I've been enjoying being working in the haptics area since I started my PhD at MIT in 1990. And when it was a new thing, we didn't call it haptics, and we called it. Well, my supervisor, Will Durfee, said, "Karon, why don't you come back and do your PhD in this new thing where we're going to take robots and have them touch people instead of other stuff. And do you think that sounds cool?" And I said, "Yeah, that sounds kind of interesting." And so no one had really done this before. Hey, so I just recognized someone in the audience. How exciting. 3 people in the audience. Sorry, 4. Oh my God. Interval research is here. What a great surprise. Okay, so anyway, okay. So we started haptics, and so that was quite a long time ago, right at the very start, which really came out of robotics engineers at MIT, where the first work, and of course it's spread quite a bit since then. And from quite early on, I was very interested in not big expensive machines, but how you could make it small and cheap and universal and accessible to people. And this was when I was at MIT and in robotics at MIT, I worked with a lot of other graduate students, and I think that there was kind of a culture there, which was that your personal worth was directly proportional to the number of degrees of freedom in your robots that you built. And, and so I was working on knobs, so I was pretty low on the pecking order. And so my life work has become to justify knobs, and knobs are cool. And knobs are hard, and there's actually, the complexity is not in the mechanics necessarily, but in all the stuff you have to do to make the mechanics comprehensible to people. And the reason I like knobs was because you could make them small and cheap and robust and out in the world, and that was actually a feasible objective. So we'll see how we're doing. That was 20 years ago. And so we've been working on designing this haptic technology for quite a while now. If I can count, we're coming on darn close to 30 years since some of the very first papers and patents were actually going out there for rendering, or just this idea of being able to display a virtual environment. And so the technology is actually finally starting to be out there, sometimes in forms that I, as a connoisseur, do not feel totally excited about or enthusiastic about, but still people start to know what the word is. They know that haptic is not a liver disease, and it's more familiar. People have usually seen it in their games, but there's huge obstacles to actually using it as a design medium. It is not at a place where, even if somehow a company has managed to put haptic actuation into a product, that their design team is able to make it feel good, make it meaningful or comprehensible in the context of an application, because we just do not have the design guidelines, the design knowledge, and there's many obstacles, there's many reasons for why that's such a challenge. So designing with haptics is different than designing with other modalities, other sensory modalities. There's ways it's the same. We have some of the same challenges, the same processes we use, and then there's ways that it has its own specific challenges, its own idiosyncrasies that make it particularly difficult. And I feel like at this point in my career, I have started to bash my head against these problems enough that I have something to say about it, have something to share. And I am now trying to collect that knowledge and make it more available to people. And one of where it comes down to is hapticians need tools, but we actually first need to understand what it is that hapticians do that they actually need to have supported. And so one context I have, so I've been an academic researcher for quite a while, and so I think about all the stuff that we do in the haptics world. And so you guys are all HCI researchers, and so you you'll recognize these things, but I just want to quickly make a point that you'll recognize. We do interaction design. So this is just some pictures from some of the research over the years. We might be sequencing human-robot interaction or trying to figure out what happens when you touch a wearable display or a communication protocol for a mouse that vibrates. Some of this stuff goes way back, but basically interaction design, like what would happen if you actually put haptics into it, and what is the story, the narrative that a user is going through. We do a lot of prototyping, okay? A lot of the prototyping in my lab is what we call haptic sketching, so quick and dirty, rough sketches, trying to get stuff very fast, to the extent of building it out of Lego or RC motors, remote control car motors, to engineering prototypes that might take several years to build. But we're trying to answer some question that way, but these prototypes take a while to build. Or we do evaluation, sometimes very arduous, difficult, complex evaluation setups where we're trying to reproduce with some amount of control, some realistic context. One of the funniest recent ones was when we're actually trying to evoke real emotion in a lab setting without actually inflicting damage on anyone. And so just kind of the lengths we have to go to construct these things. My students might spend a year constructing an experiment where we're trying to learn something, and I'm sure that this is not a foreign concept to some of you. Okay, and then we have all kinds of data. Every experiment, we're doing unique kinds of analysis. The whole point I'm trying to make here, which is probably not a surprise to you, is that we take a lot of time and effort and creativity to take every little ounce of knowledge a bit further. And if you're in industry, this is completely not available to you. Okay, this is not a luxury that you have. You have one shot at it. You have to deliver a prototype in a month. How do you actually leverage all this knowledge and all this care and all this love and creativity that we've been doing in academia and say, so what should I do to make this thing actually work? And this is a big knowledge gap that we've really been struggling to get over with. So let's look at design process. So I'm the first to start it. This is going to look extremely boring and unoriginal, stuff you've seen before. I'm trying to design a haptic interaction. What do I have to do? There's these different stages of design that we go through that are broadly accepted, although many different names. I'm not specifying anything about the order you might go through or all these other things about design framework that you guys want to add to this. But there's some basic design activities that happen over and over by any kind of designer anytime. Browsing through examples, trying to get inspiration, the process of creating and ideating, conceptualizing, iterating, refining, trying to test and evaluate and see if it works and how to do it better. And of course, the many forms of sharing, which include sharing for the purpose of evaluation, for sharing for feedback, showing to your venture capitalist or your boss or your client, or even sharing into places that other people can browse so that you're actually kind of populating the ecosystem with examples. These are all things that we do when we design, but all of these things are really hard to do in haptics because of the special characteristics of haptics. So if we try and take a deep dive into a couple of these. So browsing is one area that is particularly difficult with haptics because when you're browsing, you're looking at collections of examples. If you're trying to build a new website, probably the first thing that a lot of people would do is they go and they'll look at a bunch of websites that have some aspect in them that meets to the particular problem you're trying to design with your website or your graphical job. And one of the things you might do as a computer scientist is not just look at the surface of the website, but you might want to actually go in and say, I like that effect, I like that piece of it, how did they build that? I want to open the source code and look at it. Try and do that with haptics. First of all, you can't find the applications and the examples, and then if you can, it's very hard to break into them and see how they were constructed. And it might be a hardware thing, it might be a software thing, and it might be a whole software architecture thing about how the signals are being transferred through a whole system. Very likely, your haptics are part of a larger system that included graphics and audio, maybe virtual reality environment, and it's all a big interlinked system, and it's very hard to deconstruct all of that. So there's all these problems, but I'm going to talk about one particular problem that doesn't even get that far, which is talking about it or being able to describe it. So usually, if you're a haptics engineer or a haptics designer, you are stuck with the parameters that you have knobs to turn, okay? Which is I'm gonna talk for the first little while about vibrotactile feedback, which is not my personal favorite medium of haptics. It's not the most expressive or rich or where we want to be eventually. But for the purpose, it's sort of like laboratory biologists who study on a Drosophila fly platform. It's there, it's manipulative, it's something we can study even if it's not exactly where we want to be at the end of the day. So if you're trying to do a vibrotactile sensation, this is basically what you got. Okay, these are the knobs you can turn, that's what you can do. And then you have the end user, and the end user is thinking of things like, this is a really urgent signal, or this thing feels chunky, or it sounds like a motorcycle, or I want it to be something that I can feel when I'm running and I'm sweating and my body is moving around. And these are very different than what the designer has to work with. And so this is a big disconnect. And part of what we've tried to do is say, well, is there some way you can bridge that disconnect? Can we actually make a design language that is closer to what this guy is thinking rather than what this guy is forced to think right now? Can you let this guy work in this language? Okay, so what would that take? So this is one piece of work that my former PhD student, now Dr. Saifi, she's Max Planck Institute now, was working with a visualization expert, tried to get past the fact that it's generally, when we're feeling haptic sensations, you can only feel one at a time, or you can only concentrate on one at a time. Being able to attach metadata to them through a great deal of user studies, and then be able to visualize them not by looking at the actual signals, but by looking at their arrangement relative to each other in different facets, different ways that I might want to think about it. And so the particular facets that she came up with were physical view, emotion, metaphors and usage examples. These, after a great deal of talking to users, seem to be the ways that you could sort all the different words and terminology that people would use when she was in the context of end user customization when she was doing this. That would cover the bases. And then if you could actually rate, she created a large library of sensations and organized them. So what you see here, this is called VibeViz. It's a visualization tool that you can access online, and it's an interface to a large library and has these different views. And the little dots are the whole library in each of these views. And when you filter in one view, you can see the same filtering on another one. So it's a standard, a linked visualization. But the idea is that now you can browse and you can actually look at the same stimulus and see where it shows up relative to other things. And you can find neighbors in different places. You can drill in and look at the actual sensation, the time course of it, a graphical thing, and you can actually play it on a tactor. And so the idea is that this is a browsing interface that we then could use. It was the product of a lot of research, but then we could actually use it in a lot of research. And this highly understood library is something that we have, it's an asset that we used, and it's available online, and is actually being used by a couple of companies. So that is an example of browsing, but it has terrible limits. For example, you can't modify, you can't move. If you actually want a sensation that's halfway between a couple of things, we don't have any way, well, we do in later work, but as of the time of this library, you couldn't say I have a sensation here, and I actually want something partway in, a perceptual morph between them. And that is something that we have done since then. But editing and sharing would be another design activity that we said. So part of this was really, we were making all these tools over the years, and we started to say, well, let's actually try and locate our tools in these different design stages and see what is special about these different design stages. So that was a browse tool. But then in detail design, here's one that another recent PhD student, Oliver Schneider, built. Oliver is now on the job market, hint, hint. And he built Macaron. He likes to name all his work after cookies, it turns out. And so making a powerful editing tool, we've made lots of editing tools in our lab. This one, he had an ulterior motive. He wanted to use it as a research tool to study a particular premise, which was about use of examples in design, and see how people's design process changed depending on their access to examples, both at a superficial level and at a deep level if you actually opened the examples up. So here's an example of what a tool like that might look like. This is where
Examples
you don't.
help design. The haptic library
How's
is
the
a tool
sound
that
there?
you select. Viewing the source of an example enables much more powerful tools.
Oh,
To study
one?
this in haptic design, we built a vibrotactile editor and added
Like that?
example features. We logged user actions to capture and illustrate their design process. Finding users followed an archetypal process, with examples facilitating design and helping users learn. We also report several lessons for future design tweaks.
Okay, so the point there was that he actually made something where we actually took the same vibrotactile stimuli that were collected in that other library and made them available in an editing tool so that you can go and actually open them up. And then he actually studied through an immense amount of qualitative work, watched people on a design task and segmented the different things they were doing and looked at how the activities changed depending on their access to examples. So we found that this tool, however, was actually very effective for other things. We adapted this tool about 6 times, I think, for different other kinds of design jobs, including robot motion, expressive robot motion, when you need something as a refinement as opposed to the initial sketching part. And we have some other tools that were more for the sketching part. So that's just a couple of examples of different things we can do here. We have tools that are in all of these sections, quite a few that I can't, for time, actually talk about. But I want to talk about the create step in a different context that's not vibrotactile, which is more, we have done all this work on robots that you touch, affective robots. And I'm going to use that example to talk about the create design stage and some of the tools that we've developed there. So affective touch, sorry, giving another little bit of background. So we've done all this work on communication, functional communication with vibrotactile signals and other things. And there's immense amounts of stuff we've done on attention and learning, your ability to learn signals. And meanwhile, the whole thing about affective touch started around 2010 when I started to read and notice literature about, studies where we'd see that, people's outcomes after cardiac surgery were highly linked to the fact of whether they had a dog at home or not. And trying to say, well, was that because they took the dog for a walk more and they got more exercise, or having the dog connected them to other people and there were social attributes, or if you had a cat, was it because you had to take care of the cat and feed it and that made a difference? How much of it could have been the touching part? And if some of it was due to the touching part, what was going on there and how would you study that and can you reproduce it? And I'm just curious, okay? Didn't even have any applications in mind, we're just curious. And about the same time, I had a PhD student come and want to work with me, a potential PhD student. And his story was, this is in 2009, Steve Yohannan, he sat in my office and he says, well, I had this girlfriend and she had a cat and I really liked the cat. And then the girlfriend left me and I really missed the cat. And I'm trying to figure out what it was about the cat that was so important. And I thought, okay, we have to go down this line. That's just so weird. And of course, at the time it was kind of weird, but now there's a lot of people looking at affective robots. But that was a process where we actually went and built a number of robots over the years and tried to actually study these in a robot platform. And so I'm going to give you first the dead simple model of human-robot interaction that we proposed in 2009 and have not finished squeezing the juice out of it yet. It looks simple, but it's not. Okay, so here's the idea is that you have the person and you have the robot, and the person does this simple thing, which it's like imagine there's a dog over here, but we're making it be a robot. And you touch, you pet, you do something. You display emotion in some way through your hand to the robot. What does the robot do? The robot has to perceive the touch and somehow decide what that touch is. The robot has to decide what that touch means. What did the person intend by that touch? Was it a happy touch? Was it an affection touch? Was it a corrective touch? Is the person mad at me? Is the person trying to make me feel better? Okay, and then the robot has a personality or an agenda. If it's a therapy robot, it might be a robot that really wants to go to sleep right now, or it might be a puppy that wants to play, or it might be one that's got a job to do, which is to somehow do something with the person. And that will do, the robot then decides with whatever AI you put into it what its response to this is going to be. And then the robot has to render something based on what the robot is capable of doing, what degrees of freedom the robot might have. They might have very limited display capabilities. They might have very powerful display capabilities, but somehow robot needs to translate to, I'm going to display this emotion, and then this is how I'm going to do it given what I have available to me. And then the human does the same thing and perceives and processes and reacts. And so you have this virtuous loop going on where they're both affecting each other. It's bidirectional. And maybe, just maybe, you can actually deliberately change what's happening in here as a result of what you're doing over here. So that was the challenge we set before ourselves, and we thought, well, this is a robot, this is a machine, not a real animal. This is why we did it on robots, not real animals. So we can actually zoom in on one of these things at a time and try and break the problem down a little bit. And so we built robots, and we studied this part, and we studied that part, and then we tried very carefully to put them together and do a loop and see if we could make something happen there. And I don't have time to talk in great depth about all these things. There's about 6 or 8 papers and chunks of work and a whole bunch of robots involved here. But the answer was that, yes, we were able to break a lot of these things down, and we were able to do it. I should first back up. In this room, can I assume that everyone knows what affect is? Raise your hand if you kind of know what affect is. So most, but not 100%. So has everyone, maybe not everyone, has seen a model of affect. This is a version of one of the most common models of affect that's out there. It's a very simple model. It doesn't capture everything. It captures some things to a useful degree. So you have two dimensions, arousal and valence, which basically is saying which direction and how much, how strong. A third dimension that is sometimes used is dominance, which would be orthogonal to this. And the idea is that you can actually place most of the words we use to describe emotion somewhere on this space. Dominance would distinguish, for example, distressed versus furious, okay, where you have a more aggressive aspect to high arousal, negative valence emotion. And you can imagine when you think about a robot that you're making, you might build a robot that is capable of displaying distress, but to have the capacity to display rage or anger or hostility, you might actually need different degrees of freedom. Also, we have not yet built a robot that has teeth or hackles. Well, actually we have, but not in the main line of research. It was more offshoot. And as a result, it was very hard to do the dominance dimension. We would need to build a different machine for that. And one of the reasons for that is that one of our target audiences was kids, and it wasn't clear that we wanted to snarl at the kid. And so there probably are occasions when that would be appropriate, but like, put me down, I don't like that. But we haven't gotten there yet. So some of the challenges we have just purely building these robots and making them work as experimental machines were to be rendering a recognizable emotion state on the robot, to be able to sense the person's affect, I have a typo there, before or during an interaction, either directly on the robot or by taking other information that you might have from other sources and integrating that into the information. Our holy grail is to get everything out of the robot interaction itself, so through the touching itself, so that you don't have to, for example, making a kid who's having an emotional meltdown put on their sensors or something, which is not going to work too well, and then changing the person's emotion state. So very quickly, this is an early robot. This is not actually the first one. This is about the third one that we built. This came into being around 2010. What we had to work with then was FSRs, force-sensitive resistors, pasted on a fiberglass shell. We call this the turtle with a fur coat. It wasn't really where we wanted to be on sensing, because at the time, you can obviously see what the issues here are going to be. Not only are the problems with the tactility on it, it doesn't feel right with the fiberglass, but we needed the hard surface to get a good signal out of the sensors, which sense pressure. But the big problem was that you weren't picking up anything in between. We had accelerometer to get vibrations from taps, and that worked pretty well. But this was very unsatisfying as a sensing system, but it was the best we could do at the time with the technology, and we did a lot of research on that. You could buy very high quality flexible sensors at the time for robot fingertips, and they cost something on a few thousand per square centimeter. And when I wanted to just saran wrap a large surface, and I didn't want to pay $50,000 to do so. And so that was just not available, and I didn't need that kind of resolution. On the display side, this robot could make breathing movements. It could do something with the ears that expressed arousal, and it had a heartbeat. And it sounds very simple. We iterated a lot with many other haptic sketches to arrive at those. And you would be surprised how well it worked. Using this robot, we were able to render emotions recognizably into all the quadrants of that affect grid. And that was like, yay. But it wasn't very useful as an interaction because we couldn't move from one to another. And it didn't have the right affordances. So for example, around this time, people would come in the lab and they would see this robot and say, wow, that's really cool. And I have a kid with autism, and I bet this would really be great for them. I'm saying, oh, how? And what would you do with it? And they would say, oh, well, you should talk to my doctor, and the doctor wouldn't be a researcher, and that would be the end of it. And meanwhile, we were saying, well, that's interesting, and we got interested in anxiety disorders, and we started to work with kids with anxiety disorders. The challenge there was there was two challenges. One was that, has anyone in the room ever worked with kids in an experimental context? A few people? Have you ever had to try and change a kid's emotion? Okay, so maybe you can sympathize with me on this one. So I had a situation where, okay, I want to get a kid really stressed out and see if I can calm them down. And all under ethical review. And so we tried for quite a while. We gave it a good try. And it was, one thing was the kids don't follow instructions. I should have seen that one coming as a parent of kids in this age. But so it's very hard to make them follow an experimental protocol. That didn't go too well. But also, it's hard to actually get them into a state of deep anxiety so that we could actually then try and give them what we thought was a pill that would calm them down, essentially an interaction here. And we tried lots of things, and about all we could manage was to get them into a flow state, which worked really well, but wasn't what we were after. So we ended up going back and working with adults, which we could take more liberties with, and found some great results in terms of being able to actually change their emotional state, and discovered in the process that the breathing motions actually, there was something going on with the breathing that was very powerful and very hardwired, and so much so that we now have another spin-off project, which is in its final stages of clinical trials right now in the pediatric intensive care unit at Maine Children's Hospital in BC, which is basically this thing turned inside out. It's now just a platform that goes up and down, and you put it in the incubator that a premature infant, which might be this big, is lying on. And when the baby is stuck with needles and cause pain, which then cause brain damage, slight cumulative brain damage that leads to negative outcomes, this breathing motion actually mitigates those pain responses, and the baby does not have those adverse effects. And there is something about the breathing, and we thought of doing this because the standard of care has become actually lying the baby on the mother's chest. And we basically have shown that we can get the same benefits in a premature infant of being on the mother, of being on a moving platform. So can we actually duplicate and reproduce some of the effects of haptic touch with a machine? It appears that we can, even if you don't have any emotional attachment to the machine and it's just a hardwired motion. At this point, we thought, well, we need two things differently. We need interaction design. We need to actually, so one of the things we learned from the kids was that when you show them the robot, this first one, I could show them this one, and they say, oh, I love it, and I want to pick it up, and I hold it, and they talk about it, and then they say, where is it from? What is it? Why doesn't it have any eyes? What is that cord? What's tail? Why is its tail plugged into the wall? That's a data and power tether in this case. And when I turn the power off and the engines die and the thing kind of goes, bleh, they say, oh, it died. and we realized pretty soon, it's like, oh, we need a narrative. The narrative is really important for this robot. And people bring a story, or you have to give a story. It doesn't matter. There needs to be some kind of a story. And later, more recently, there's a paper we have at Chi coming out, which we've taken this line quite a bit further, is that we can have a very strong influence on how you interpret the emotion rendering based on the narrative that is applied to the robot. So any ambiguity gets resolved by what the person thinks is going on, and either the person brings a narrative or I give the narrative, but there is a story, and that is the frame in which you interpret what's happening here, which is exactly what people do. If you're trying to decide when your partner comes down for breakfast in the morning and they're grumpy, Are they just tired and had a bad night's sleep, or is he mad at me for something? Will be dependent very much on whether we had a fight the night before or not, for example. Like, I might bring a narrative to it which helps me interpret, and then how I resolve the ambiguity is I will probe, I will inquire, I will ask something, I will say something that will then the response will help to clarify it. And so we started to do our interaction design thinking much more about narrative context and probing and interrogating and resolving it that way. So we wanted to do interaction design instead of rendering these static emotions. And so we needed to say, well, okay, we developed a new use case, which was we're trying to access stressed out kids. We found a great solution, which was actually to go into the children's intensive care, the waiting room for pediatric surgery. The anesthesiologist wanted help. They said, the kids come in, they're terrified, we have to stick a needle in them and make them go to sleep, and if they fight us, this is bad. They don't go under easily, and then the surgery doesn't go as well, and the recovery is not as good. If we can actually calm them down without having to give them drugs, that would be great, and if you have a way to do that, that would be awesome. So we said, great, we don't have to stress the kids out, they're already stressed out. And so are their parents. Their parents are the ones who are really, actually one of the things I figured out is the parents who need this more than the kids. And the parents are making the kids be stressed out. So remember that if you have a kid going under surgery. So we thought, well, if we're going to do this in this environment, we need a real robot, not just one that computer science grad students are building. And so we went to a professional design firm and said, we want this thing, and I can give you engineering specs, but I'd rather we kind of figure out, open the box and try and think of new ways to do it. It needs to breathe, and it needs to kind of huddle, and it needs to be able to be open and for business, kind of yoga-inspired movements. And it needs to be able to give an orienting response, all of these things, and help us build it. And the engineering firm they thought this was a really fun project. They usually built medical instruments and things like that, so the hospital environment didn't faze them at all. But they really did not have the right process for this, and were not able to do an iterative, lots of sketching and then converge on expressive design. Because we were really trying to design expressive movements, and it was very hard to give strict engineering specs for that. So this was a very expensive learning experience for me. And so we never have used that robot in a study. Instead, we decided to go back. It was not effective in displaying emotion. It was just kind of weird. The things didn't work together. So we embarked on a whole nother journey, which was to let's just take 1 degree of freedom at a time and just really understand all the things you could do with it. And for that, we needed to do a very iterative process. So go to town. And we wanted to do things that would be quite I don't think this one has sound in it. So this was at Chi last year. And so this is my student, Paul Bucci, mostly, along with a couple of other students in the group. And the idea was to use haptic sketching and actually develop design systems that we could quickly iterate. So even you bring a subject in and they didn't like something, we could build another one right on the spot, or even, or perhaps coming back the next day. And so what he had to do was he spent a whole lot of time just trying to figure out the kinds of movements that would be expressive. These design studies that I'm showing you here are about breathing. We're currently doing design studies on many other degrees of freedom that are displaying other things here. So we're talking about periodic motion that might express things that would be recognizable from mammalian breathing. And so he ended up coming up with a couple of models, and the idea here is that you want something that's very cheap and quick to iterate, but also is robust. And so generally he went to this family of flexures. So there's some compliance in the mechanism, in the body, and it wants to spring back to a particular shape, and then you use the motor to push against that, so it has a passive state. And then what you have is this really cheap motor that doesn't have to be very fast or good, it can be super simple, that is working on compression, and therefore you can throw these things against the wall or step on them and they won't break. They're very tough. And they're cheap, and a kid can make it. We have kids camps, and they come in and they get to make their own cuddle bots, and they can customize them, make them different. They're really easy to make. And so there's a couple different systems here. One is made out of wood pieces that you can laser print and laser cut and iterate very quickly that way. You can scale them or put little features on them or make them lopsided or whatever. And the other is just made out of plastic that you print on a piece of plastic and then cut out. And so they're pretty quick to iterate. these design systems. But at the same time, we're realizing that, so one of the reasons we wanted to iterate so fast was that the behavior and the motion need to be designed at the same time. So how it moves and how it can move. And it turns out it's very hard to tell. Now, we saw all those motions. How did we actually create those motions? Well, it's not so easy. And one of the things, for example, that we saw that people really wanted to do, we bring subjects in and say, how do you want it to move? Or if you want it to show that it's scared, what should it do? And they would say, oh, I can't program it in code. And they would start vocalizing. They would make, I want it to go like this, or I want it to do this sound. And they would use their body to make these sounds. And so we went with that. So these are some of the different tools we actually use, including using audio to source sounds and then play those out as a starting point, or the verbalizations. And I'll just show you an example of one project which was about using voice.
Vocal doodling for effective robot interaction. When describing something abstract like motion, many people may find themselves at a loss for words and may opt to use non-word vocalizations to express themselves. Voodle translates the properties of your voice into motion on a 1 degree of freedom robot. Voodle detects features like pitch and amplitude and interprets them according to a set of user-definable parameters. With Voodle, users can quickly and naturally sketch effective behaviors in a unique conversational design space.
So I was really proud of that project. That was an undergrad researcher who did that and presented it at DIS last year, and it got a prize, so that was kind of fun. So what you see there is this really difficult step. Oh, and I've demonstrated this work myself at a conference, and I can separate the world into people who will bark at a robot in public and people who will not do that under any circumstance, but love to watch other people doing it. Just another category. So, and then, okay, we talked about experimentation. So when we're trying to decide how expressive it was, so this is one of the kinds of studies we do where we did a participatory design with professional voice actors, people who are actually good at modulating their voice. I think one was a singer and 2 were actually theater people. And so we take our 2-dimensional affect grid and say over 3 sessions where they would play around with this system and then say, I want you to change the system to make it more expressive. And they would actually say, well, what if you do this with my voice, and I want a robot that can do this? And we would iterate on both Voodle and the robots, and they'd come back and they'd do it again. And this is just showing that over 3 visits, they would draw, these are the spaces on the affect grid that they felt they could reach if they wanted to do something, they could make the robot do that. They had that expressive control. And you can just basically see that over time with these iterations through some hard to quantify combination of experience and improvement in the tools and the robots, they were able to get more proficient or more capable of it over the time. So that would be a create tool. So the combination of Voodle and the whole Cuttlebit system and all this was this whole big launch to try and say creating expressive movement. Now, if we want to edit that movement that we've sketched, then we use something like Karon, that editor, and go and tweak it. Once you've laid down the first track, you want to go in and tweak it. So that's one thing. And so I just want to touch briefly on the sensing side, which I talked about this bottom part of the display. So here's, I showed you those FSRs on the, is that actually playing? So this is a fur sensor. So we had this problem of wanting to really pick up delicate touches. So this work is by Anna Flagg, who is a master's student who's now a reporter for Al Jazeera. So you can actually see that she went a different direction after this. But she's, you would see how this works, or guess how it works? So this is actually inspired by some work by Leah Buckley at MIT, so this photograph is Leah's work, not ours. I need to do a better job of showing that on this picture. But the idea was that you actually have a piece of fabric. This is conductive thread that you've woven through it. You have collectors at the end so you can make a circuit. And the way you change the resistance across this very simple circuit is you scruff the threads together. They have different amounts of contact, and that changes the resistance across the circuit in a stochastic way that you can then train. So that's what she did, says, oh, look, you could make a resistor that changes. What we did was we took it a whole lot farther and applied machine learning to it and actually showed that you could actually distinguish lots of different kinds of touches by training it. And the devil is in the details to actually turn a very simple concept into an effective sensor by getting the exact proportions of threads and how that all works. And we found it worked best if you have varying lengths of threads, and it's more expressive, and you can actually collect a lot more detail. And so early on, when we had the first robot, we developed something we called a touch library, a touch dictionary that had, I think, about 80 touches, all the different ways that people ever touched our robots. So we collected frequency data of it from all kinds of video studies. And these are the highest frequency touches that people would make. And so we kind of take this smaller set to do a lot of our studies. And so what we saw with this sensor is that this is the kind of recognition accuracy that we could do on touches, of these different kinds of touches. So basically almost 100% distinguishing using this simple sensor. But this is a really cool one. Like that we were hoping for. This one was a complete shock. So here's the different touches. I think this had 15 subjects. This is how well we could tell which person was touching it. So not only could we always tell what touch was being made, within that, there was enough individual difference in way of touching that we could say who was touching it with not very much training. So that was actually like, wow, you could actually have the robot just from touch, not from sound or voice or anything like that. We actually know who's petting it right now, and that's pretty interesting. We went on to make a different kind of sensor as well. This is a very inexpensive fabric sensor that uses electrically striped fabric in different layers, and you make taxels that are about a finger pad size large, and just saran wrap robots on it. So we've come a long way from the FSRs, and we're now also collaborating with a group in Germany at Max Planck who is doing the same idea, but in printable electronics that are gels that you can just layer onto things and are more customizable this, and working on making different shapes and kind of make design tools to actually print these sensors. And so we can do all kinds of stuff with that. So I'm out of time, so I won't go into the many things that we're doing here, but these systems that are then customizable and working on making tools so you can actually design and print these sensors and put them on different shapes. And then you can, not just on robots, but on different objects. So you might want to have an object that I put in my pocket and I fiddle around with it and I can tell your emotion and do some kind of intervention because of the way you're fidgeting with something. That's one of the things that we're actually going for here. And then have these in a way that people who want to play around with it can customize it and do their own version of it. So trying to go back to the accessible haptics, we have all these tools, okay, that I can, link into a design framework and say there's these different kinds of things, different design stages that we use. There's a lot more that I didn't talk about here. And these are all, we put them on our website and we've got them on GitHub and people can do that. But how can we really help people design better? And so the next kind of phase of research that we're really trying to do now is really to go directly at the problem of making it accessible and putting out there. And understanding designers, we've done some studies of designers, but now we're trying to look at different kinds of designers and trying to create an online repository of tools that people can build and customize and develop so that we can start to break this obstacle of creating content and creating devices. So trying to make, oh yeah, this slide is messed up. Okay, so thinking about the design ecosystem, which differs by what your design purpose is, what your knowledge and background is, and but giving access to it. So for all these, this is the framework, and we're trying to support a larger audience. And so we're developing an open haptic repository. You won't find anything at that location yet. It's under development. But the idea is that so far we have a lot of haptic devices. We have a lot of tools. We're trying to bring other people into it. It's not supposed to be just our work. The whole point is it's going to be a public open access thing. I just spent the day yesterday at Mozilla actually talking with them about how you launch a system like that and what role they might like to play in helping us launch an open access portal like this. More of an Arduino model where maybe you download designs yourself or you can have someone pay for them. These are some of the things that we're working on right now that would be part of the population here. So we have hardware, a few pieces of hardware that I am not talking about right now. Some of it were, actually both of these things we're demonstrating at the Haptics conference in March in San Francisco, which I can give a plug for if you want to go up there. There's software, so the back-end software that lets you actually prototype things on devices that you may have made yourself. We've run student design challenges where we put those tools out there and support student designers and then actually study the student designers to see what kind of problems they have. Plus, the student designers generate all these designs that we can then also post. And Haptic device library. And this is a case where we've been very frustrated that there's all these, going back to the 1990, all these inventions that people have made of haptic devices. And I've long enough in the tooth now that when young people come to me and say, Karon, can you tell me all the pantograph designs that are out there? And I'm going, I know there's 5 or 6, but I can't even remember who they all are. And that's like one of the most common mechanisms. There should be an online place where people can go and browse. A lot of this stuff was actually invented before those papers are not even available online, so it's very hard. And so instead, people have to go and invent it all over again. And so we're trying to figure out, if you find all those inventions and you post them, how can you visualize and browse them? So if I'm looking for something like, I want to make a wearable device and I want these attributes and I want to find designs that are suitable for low power wearable applications in a particular way. And you want to find stuff where the original designers weren't thinking of those attributes when they did it. So we're trying to collect the designs and then expert source annotations on them so that we can actually visualize and browse these kinds of things. So it's actually a big community project that's involving the whole haptic design community to help contribute annotations as well as designs. And then a big project that actually started with Allison and Okamura here at Stanford, but we're continuing on our own, is educational tech that helps people learn physical concepts using haptics and understanding the value of that by working with educational experts. And now we have all these different designers, which are the students who are playing around with stuff and building systems they're going to feel, the teachers who are helping to build the sandboxes, and the third-party designers who are trying to contentize them and do this all with extremely low-cost technology that could be successful in a classroom environment. So that's another big push that we're doing, and will be a driver for some of that. So that's where I'll stop. And I just wanted to do a little plug. We're doing a big development at UBC, which is the Designing for People research cluster. We have a new graduate training program for PhD students and advanced masters who want to do research. So it's not an industry professional masters, it's really for researchers. And it's very interdisciplinary. You guys have a great interdisciplinary group, but I can go one better. We actually have 8 departments, not 3 or 4, and we have about 80 or 100 people coming to our lunch sessions, which are only once a month, not every week. And so what we're really trying to do is band together to both solve these hard interdisciplinary problems and have collaborations to do that, but also to help train graduate students in a way that they can integrate those different perspectives and really take these very broad views, and to help with this knowledge mobilization issue where we have all this knowledge that we're trying to get out there in the world and trying to find different ways to capitalize on that by working together. So there's a lot of activity going on in that at UBC right now. So I'll stop there, and hopefully you guys have some questions. My students. Hey, Sean.
Great talk. Really exciting work that you've been doing. I was wondering if you could talk a little bit more about, I know you didn't talk about it in this talk, but about how the studies you've been doing about context and effective display of haptics, and how that changes perception. And so how obviously our perception is guided not only by the sensory information that we have, but also the context in our understanding. But I'm also wondering, like, how far in the stuff that you guys have done so far, how far can you push it in terms of changing the perceived affect based on just the story or the context?
Yeah, there's 2 ways to look at this context question, and one is in deep frustration. It's like, man, it's really hard to control what people sense because the context, like if I can't control the context, I have no idea how they're going to interpret it. So that's kind of a discouraging way to think about it. And then the other way is like, wow, I can really get away with a lot in the haptic display because context is so important and you can actually dominate it. But then you need to have some insight into what the context is or some way of controlling it, or the approach that we're taking is more to try and think of it as interactions where people will reveal more and interrogate and follow up, and that it's something that actually has to take place over time. So the long-winded answer, I show you this affect grid of kind of these discrete emotions, and we've really, over the last few years, have started to say, that's really not a very useful for real situations. Real situations, you're feeling complex emotions, multiple at a time. It's not like, oh, right now I am sad, right now I am happy. It's, I might be both of those things at once. And what we're really looking at more is deltas. So if we can actually detect changes over time, then that's where the dirt is. That's where the interesting stuff is. And so we're very much trying to detect alterations and then be able to interpret those in terms of context. So we've really departed from that original one, although it is a kind of a grounding and a way of talking about it and organizing your thoughts still. In terms of the narrative, it's funny, just again at my foray at Mozilla, this stuff is already coming up all the time, all this stuff with IoT and networked IoT and being able to collect information from different sources. So we've focused more on touch because that's kind of where we started. But there's a lot of information from other sources, including vocal prosody and stuff you might getting from imagery and video cameras and history, knowledge, past knowledge of a particular individual. And some of the scenarios that we have are for maybe putting these robots with a child, and the child is carrying around like a stuffed animal. And over time, you could build quite an elaborate profile about patterns in the child's life. And I think that if you had that and you could stomach all the huge ethical issues that you're dealing with at that point, you could do some really amazing things in terms of being able to intelligently infer what's going on. That's getting much deeper into the AI than I am the expert on, and so that, for me, this would be collaborations with other people who do that more. But I think that is, if we're trying to make extremely rich interactions, that's kind of the direction you're going. I think it is, being the patterns and personalization, actually understanding a particular individual, it's going to be very important. Yeah, so not a very satisfying, but can keep us busy for a long time in the future figuring it out. Yes?
Could you tell us a little more about why you initially chose ears as the primary mode of expression and how it currently compares to something like breathing, which seems to be more effective?
Yeah, so we wanted, of course we were doing ears and breathing. And strictly speaking, they're not ears because we actually tried very hard to have it not be representational. And if I could show you some pictures of some of the earlier prototypes, we made all these sketches, and we kind of figured out fairly early on, we made many different shapes with many kinds of appendages on them. And we were trying so hard to have them not look like real animals. We actually put these bumpy things at like either end of a body, so that it really didn't look like ears at that point. And the feedback we got from people was that, no, there needs to be two and they need to be next to each other because that's what I want to do. I want to kind of stroke them like a dog's ears. I said, okay, user-centered design. We will put the ears together, and then it looks like it has a head, and you're kind of stuck with that. So the reason we didn't want to have a head was because we were trying to really focus on the haptics and the touch, and so we were trying to not make a visual focal point on the object. Of course, now as we're going into these more interaction design things, it is actually helpful to have a visual. For example, in the hospital environment, we will have a situation where the first stage of the interaction is actually getting the kid to pick the robot up. And so that's all visual. So now we're working on visual gesture. At some point, you transfer over to haptic gesture. And so the ears are a useful tool because they're very recognizable as a way of indicating attention and arousal level. And so they're just, we are so well trained to understand and interpret ears that they're just very useful that way, both for touching and looking at. So we've kind of stuck with them. The current robots, the big degree of freedom that I'm really excited about right now is a spine. And so being able to do this versus do this and have that integrate with the breathing and still having a very simple mechanism. And so we're doing a lot of form studies to first get the spine right. We've got a pretty good spine that does all that, but now we're trying to make it work with the ribs breathing at the same time and have that be very, very low degree of freedom and very simple to build. So it's really, I guess, the degrees of freedom are very much out of how people interpret them and being able to cover the bases on the different kinds of things we're trying to express with it. And ears turn out to be useful, and so does spine, and so does breathing. Yeah, pulse, not so much. People say pulse and heat. Those are the most common questions I get. And you think about pulse and heartbeat, and you think, well, how often can you actually feel the pulse or heartbeat in a creature that you're interacting with? And it has to be pretty upset before you can actually feel the heart pounding. And so we actually found that that's not as useful a degree of freedom, but purring is super valuable. You can do lots and lots with purring, and it's very complementary to breathing. So and it's very easy to do. You can just make it rumble, so that's a keeper as well.
I
Yes.
just want to note we're at time, so I think we'll take the other questions offline.
Okay.
Please just come up to the front. I'm sure she's happy to
Yeah,
answer
I'm very
more
happy
questions.
to continue the conversation.
Thank
Thank
you.
you.